Here we will continue the module for Commercial Mechanical Inspector M2 Ventilation. We will continue on Module 8, Required Reference, in Chapter 4, in International Mechanical Code. Ventilation. Occupants in building must be protected with the control of indoor air quality. Illustration 8a, ventilation. Occupied spaces are ventilated to promote a healthy and comfortable environment. Unoccupied spaces are ventilated to protect the building from excessive humidity and heat. We'll cover code requirements for ventilation and depth. Understanding the field. Ventilation specifically refer to fresh outside air provided to the interior building.
Or otherwise harmful substances to reach the need for ventilation. Ventilation is both necessary and desirable for the control of air contaminants, moisture, and temperature. Ventilation of specific occupancies is necessary to minimize the potential for toxic or otherwise harmful substances to reach dangerously high concentrations in the air. Ventilation serves a number of critical purposes, and this is why the code regulates it.
General requirements. Every occupied space requires ventilation while occupied. This can be accomplished naturally by opening a window or a door, or mechanically by using a barred fan. Mechanical ventilation, not natural ventilation, is required. Dwelling unit with infiltration less than 5 air changes per hour, tested at 0.2 inch water column. 2. Ambulatory care facilities and Group I2 occupancies. Do you know air will seep into spaces through infiltration? This is the amount of air that comes in through small permeable opening in the exterior of the building. Total air volume of this room equal one air change. The air change per hour equal number of room volume per hour. Illustration 8b, air change. An air change is the total volume of space or building, so to have 5 air changes per hour, infiltration means that 5 times the total volume of air in building has come in through the exterior of building in 1 hour. Air intake opening, air come into building through air intake opening. The outdoor air intake opening for ventilation must meet all these code requirements. Study tip, air intake ventilation requirements. Number 1, must be at least 10 feet away from lot lines or other building. Number 2, must be at least 10 feet away horizontally from any hazards or noxious containment source, or at least 25 feet vertically above or 3 feet vertically below the source. Number 3, must be above flood hazard level. You can refer this in the IPC section 1612. Number 4, must be protected with corrosion resistance screens, louvers, or grills. Number 5, for residential occupancies, opening in those screens must be between 1 by 4 inch and 1 by 2 inch. For other occupancies, opening should be 1 by 4 to 1 inches size. Natural ventilation. Natural ventilation of an occupied space is accomplished through windows, door, louvers, or other openings to the outdoor. The building occupants must have access to control the opening. For here, this outdoor, this natural ventilation, at least square feet of window opening for every 100 square feet of floor for natural ventilation. Illustration 8C natural ventilation opening. The area of the ventilation opening to the outdoor must be 4% of the total floor area ventilated. If there are rooms without opening to the outdoor, they can be ventilated by adjoining spaces that does not an outdoor opening with an opening between the space of at least 8% of the interior space floor area. Understanding design for an opening below grade horizontal clearance of 1.5 times the opening depth is required. Example, the owner of a new building is choosing to use natural ventilation to meet ventilation requirements. Most of the spaces are exterior and have window to the outdoor. However, there are some spaces that are interior. In one case, there is an exterior room that is 200 square feet with another 100 square foot room connected to it. What size does the opening of the window need to be in 200 square foot room? Let's see the answer. The answer 12 square feet. The total floor area ventilated by the window is 300 square feet. 4% of 300 square feet is 12 square feet. Additionally, the door or other openings between the two rooms need to be at least 8 square feet, 8% of the 100 square feet. Mechanical ventilation. Mechanical ventilation will take up near the remainder of this module. There are formula and restrictions we will cover so we understand the scope of the code and how to apply. Follow along carefully as we walk through the remainder of what is important. What is the ventilation accomplishing more specifically?
What is ventilation accomplishing more specifically? Before we get into the details of ventilation, we need to talk about what ventilation is trying to accomplish. People inside buildings exhale carbon dioxide as a waste product. If there's no fresh air, the carbon dioxide can be poisonous to them and others. Also, people emit odors. For that matter, so do a lot of finishes and furniture, plastics, electronics. That's all without talking about cooking in kitchens, the smells of restrooms, the humidity from swimming pools, chemicals from janitors' closets, and on and on and on. This is why we ventilate. Mechanical ventilation is provided to remove all the smells and carbon dioxide and other airborne contaminants from a building and replace it with breathable outside air.
Understand the practice. Except for in some small residential occupancies, ventilation must be provided through supply and return air or exhaust air. The supply air is required to have a minimum amount of fresh outdoor air to control the concentration of contaminant in occupied spaces. A prescriptive path to clean indoor air. The code contains a prescriptive path to achieve clean indoor air or an engineered ventilation system is also acceptable if it is demonstrated to be at least as good as the prescriptive path. So what are the prescriptive code requirements for ventilation? The code says this: the outdoor is required shall not be recirculated. Understanding these requirements.
Understanding this requirement. There's not really any way to control the outdoor air from getting mixed in with the rest of the air and getting supplied again for spaces that have recirculation. What is meant by this regulation is that outside air must be provided to each space straight from the outdoors at the prescribed rate.
Study tip: condition prohibiting air circulation. Air cannot be recirculated from one dwelling to another or to the similar occupancies. Air cannot be recirculated from a swimming pool to other space unless humidity is controlled to 60% or less. Air cannot be recirculated from a space that is required to be exhausted by note B in table 403.3.1.1 to another space. Take a look at this table for your reference. A maximum of 10% of the total airstream going into other spaces can be air that has been recirculated from space that is required to be exhausted by note G in the same table. Prescriptive code requirements for ventilation, International Mechanical Code, section 403.3.1.1. Now we will walk through the steps for applying a prescriptive code requirements for ventilation. Study tip: this process, like sizing gas pipes or vents, and is not something you are expected to replicate. The steps are presented for those that are interested, but for the purpose of the test, focus on how to look up values on the table and how to make some of the sample calculation. We will help you with through the quiz and the practice test. Take your time and follow closely, referencing the table.
Using the terms room, space, and zone. In this example, we use the words room, space, and zone. Rooms and spaces are used interchangeably, although rooms are typically contained within walls, while spaces might be a portion of a room or an open area that is dedicated to a different purpose than the rest of the room. A zone can be multiple spaces or rooms, or just one space.
Step number 1, determine the minimum ventilation rates for each space. International Mechanical Code 2021, section 403.3.1, table 403.3.1.1, minimum ventilation rates. In the crux of the ventilation requirements, note that this table is found under section 407 in your International Mechanical Code. For a given space, first find the occupancy classification that best match. The second column is used to determine the number of people in the space. Study tip: the occupant load from the table must be used unless there is statistical data showing the accuracy of the alternative occupant density of an architecture design shown a number of seats could be used. The third column is the amount of air required per person, and column 4 is the amount of air required per square foot of the floor area. The last column only applies the spaces that are required to be exhausted. Examples: there are two zones in building. Zone A is office space and Zone B is a conference room. What are the minimum ventilation rates for each space? This is a zone, Zone A, Zone B. We'll check for office and for conference room. For office, we'll find the outdoor rate is 5 CFM per person, and the area outdoor rate, it will be 0.06 CFM square foot. and for the conference room also. Illustration 8D, people outdoor rates and area outdoor rates in the example. This table we have created takes the example above and fill in the necessary information. Here we can see minimum people outdoor rate and minimum area outdoor rates determined for both zones. The table is the easy part. If it were left at that, then it would be easy to calculate the amount of outside air required and demonstrate compliance, but it gets more complicated. Step number 2, calculate the ventilation required for bracing zone. This is International Mechanical Code 2021, section 403.3.1.1.1.1. The value in table 403.3.1.1 only allow us to calculate the amount of air that it is required in the bracing zone. Don't confuse the bracing zone with the zone as we defined above. Defining terms. The bracing zone is the volume in the space where people will normally be bracing. The bracing zone is defined as the space above 3 inches from the floor up to 72 inches from the floor and more than 2 feet away from the wall. Think about it, visualizing the bracing zone as a smaller space within a bigger space. If you are within 3 inches of the floor, above 6 feet from the floor, or less than 2 feet from the wall, you are outside the defined bracing zone, but that doesn't mean you need to hold your breath. The bracing zone is just where we are trying to deliver the ventilation. The calculation for ventilation required for bracing zone is fairly straightforward. 1. Multiply the number of people in a room by the outdoor airflow rate per person. 2. Multiply the outdoor airflow rate per square foot by the floor area of the room. 3. Added A and B together. Here is the equation. VBZ RP PZ plus RA AZ. RP, people outdoor air rate, the outdoor airflow rate required per person, taken from table 403.3.1.1. BZ, zone population, the number of people in the space or spaces in the zone. If the population is knowing, it can be calculated from the second column of table 403.3.1.1. RA, area outdoor air rate, the outdoor airflow rate required per unit area, taken from table 403.3.1.1. AZ, zone floor area, the net occupable floor area of the space or spaces in the zone. Example, continue. Zone A, the office space is 1000 square feet. Zone B, the conference room is 400 square feet. What is the ventilation rate required for the bracing zone? For zone A, the occupancy, it's office spaces. Zone floor area, AZ, it's 1000 square feet. Zone population PZ, 5 people multiplied by 1000 square feet is multiplied by 1000 square feet equal 5 people. Okay, 5 people. People outdoor rate 5 CFM per person. Area outdoor RA 0.06 CFM per square feet. Bracing zone outdoor airflow 5 CFM per person multiplied by 5 people plus 0.06 CFM per square feet multiplied by 1000 square feet equal 85 CFM. And here also same like for zone B, conference room. Illustration 8E, bracing zone ventilation rate on example. Now we added the bracing zone to our table for both zone A and zone B. Step number 3, determine the total outdoor air to be delivered to the zone. Now that we have the amount of air that need to be in the pressing zone, we need to determine the total outdoor air needed for the entire zone. This is done by each zone individually. Think about it. What happens if our air distribution within the space isn't efficient and some of the air bypass the pressing zone and goes right back into the return or exhaust? This is where zone air distribution effectiveness come in. International Mechanical Code 2021 section 403.3.1.1.1.2. We will look up this effectiveness in your International Mechanical Code table 403.3.1.1.1.2. Understanding the code. Generally, if the air crosses the entire pressing zone, the effectiveness is 1. Some in-air system configuration are more effective while others are less effective within the entire system for a particular zone. Table 403.3.1.1.1.2 lists the differences. Note for table 403.3.1.1.1.2. Let's review some case notes that we have pulled out of this table. Study tip: read throughout lists while you look through the table so that you understand how the effectiveness is being applied to different steps. Study tip: important notes from table 403.3.1.1.2. Cool air falls, so distribution of cool air will have an effectiveness of 1. Displacement ventilation can have an effectiveness of 1, 2. Warm air rises, so putting the return in the floor has an effectiveness of 1. Warm air rises, so if the supply and return are in the ceiling, the effectiveness is 0.8, unless the air isn't too warm and less than 15 Fahrenheit above the space temperature, and it is blown down at 150 feet per minute within 4.5 feet of the floor. Then the effectiveness is 1. A floor supply of warm air and ceiling return could bypass the entire space in a halley. The effectiveness is therefore less at 0.7. Think about it. The air discharged from the floor grill is blown upward. If it's hot and hot air rises, it's then taken into the return and the ceiling. But in case such as this, the air doesn't spend much time in the space, so it doesn't have time to move into all corners of the space. This is therefore not very effective for ventilation. Total outdoor air, International Mechanical Code 2021 section 403.3.1.1.1.3. The total outdoor air that must be provided to a zone is the volume of outdoor air needed in the pressing zone divided by distribution effectiveness. Here is the equation: VOZ equal VPZ divided by EZ. Example continuation: the air in the office and the conference room is ceiling supply and ceiling return. The worst case distribution effectiveness is for heating. When does the distribution effectiveness is 0.8 as opposed to cooling, which has a distribution effectiveness for the configuration of 1. For zone A and zone B, zone A is office space and zone B is conference room. This is the same table. Illustration 8, if outdoor air flow for zones in example, as we built our table for pertinent information, we now add the required outdoor airflow needed for the both zones we have in the equation. Step 4. Determine the total outside air required for the system. International Mechanical Code 2021, Section 403.3.1.1.2. Illustration 8G. The total outside air required for the system. Now we must determine the total outside air required for the system. This depended on the system type. Okay. Illustration 8H, single zone system. Here the single zone system. Fresh air, here air filters. Okay, and here the chilled hot water out, chilled hot water in. Okay, it's going to the fan supply, and this is air conditioned zone going outside to return air. It gives some recirculation air again to the air handling unit, and the exhaust valve is giving some of the air outside. This is the single zone system. For a single zone system, the total outside air is the zone outside air. The total outside air being the zone outside air is expressed by this equation VOT equal VOZ. Illustration 8I 100% outside air system. As we see here, this is from fresh air and this is the filter. Okay, and the heat exchanger air to water, and here shielded water in and chilled water out. Fan supply air to conditioning, but the return air going all of it, all the amount is going outside, nothing give back to the system. This 100 outside air system. For 100 outside air system, the total required outside air is the sum of the required outside air of all zones. This is expressed as this equation VO2 equals summation of VOZ multiply zone recirculating system. International Mechanical Code 2021 Section 403.3.1.1.2.3. For multiple zones recirculating system, it gets a bit more complicated. Here, this illustration AJ, the multiple zone recirculating system. Here is the multiple zone, we have so many zones. Okay, here we have filter and preheating coil and variable speed supplying fine cooling coil give all the zone, and after this giving to variable speed exhaust fan. Okay, here this damper. Okay, here this is the pressure gauge for all the zones, and here is sensor for each zone. Okay, and this is terminal units, and here this is the dampers. And multiple zone recirculating system is one where a single air handler pull return air from multiple zones, mixing the return air with outside air, conditions the air, and redistribute that air to zones which have their own control of supply air. The total outdoor air required by the system is calculated by the following steps. Steps for calculating the total outdoor air required for multiple zone recirculation system. Number 1, calculate the primary outdoor air fraction for each zone. Number 2, determine the system ventilation efficiency for the maximum outdoor air fraction. Number 3, calculate the building population diversity. Number 4, calculate the total uncorrected outdoor air required. Number 5, calculate the total system outdoor air by dividing the uncorrected outdoor air required by the system ventilation efficiency. Let's walk through these 5 steps together as we continue with our example. Step 4A, primary outdoor air fraction. This International Mechanical Code 2021 Section 403.3.1.1.2.3 3.3.1. Each zone served by multi-zone air handling unit receives primary supply air VPZ to cool or heat the spaces. Think about it. The amount of primary supply air required to determine by load calculation and is going to depend on the load in the spaces. In the space, people, equipment, exterior wall, windows, etc. and will depend on the temperature of the air being delivered. Understanding design. The primary airflow is not determined from the code. The primary airflow is determined by a designer or engineer, usually with the help of load calculation software. The fraction of the primary air that has to be outdoor air, ZB, is found by dividing the zone outdoor airflow, VOZ, by primary airflow. The equation look like ZB equal VOZ by V divided by VBZ. In our example, zone A and zone B are conditioned by the same system. Zone A and zone B. Illustration 8K is a multiple zone requirement for the system. Okay, zone A required 900 CFM to condition the space and 106 CFM for ventilation as per the calculations. Zone B require 500 CFM to to condition the space, but require 155 of ventilation air. We have added this to our table. Think about it. It's easy to see if a 12% of the system supply air outside air, zone A will get the required outside air, but zone B will not. If 31% of the supply air is outside air, both will have the outside air requirements, but there will be excess outside air provided to zone A that will be brought back into the return air without having lost its outside air refreshness. That unconsumed outside air can be used again for ventilation. Therefore, the overall fraction of outside air required by code at the system level will be somewhere between 0.12 and 0.31 with no diversity. Step 4 C below. Step 4 B ventilation efficiency. International Mechanical Code 2021 section 403.3.1.2.1.2.3.2. We need to determine the system ventilation efficiency EV from the maximum outdoor air fraction. The maximum in our example is 0.31 bigger than 0.12. Look up the maximum on the table 403.3.1.1.2.3.2 now and find the efficiency EV. Think about it. 0.31 is less than 0.35 but larger than 0.25. So the system ventilation efficiency AV is 0.8. Interpolation is allowed, so the efficiency can be calculated as 0.84. Step 4C population diversity. International Mechanical Code section 403.3.1.1.2.3.3. We need to calculate the system population diversity D. The system diversity can refer to population or any other loading of the system. Diversity refers to how the sum of individual load are reduced to
An example
size
of diversity.
in larger.
The easiest example is your home's electrical supply. You might have a 100 amp service going into your home. If you plug in every device that you own and turn them up to full power, then turn on all the lights, run every appliance, every power tool, and all your HVAC equipment at the same time, what's going to happen? In most homes, you will trip a breaker. It could be the main service breaker or one of the smaller breakers. You might be outraged at this, thinking that the system should be sized for you to do everything you want to simply because you were provided with all of the outlets that you have. But most people are used to this from an electrical perspective. The fact is, the electrical system wasn't sized for everything running at the same time because the design accounts for diversity. The assumption that you don't need the service designed for you to run everything at once, like the microwave, oven, your table saw, compound miter saw, your sound system, your air conditioner, the furnace, washer, dryer, hair dryers, plus all your handheld power tools at the same time.
Understanding design. If all your devices added up to 200 AMPs and your devices is 100 AMPs, the diversity is 0.5 or 50%. The design is only 50% of the sum of the parts. The sum thing goes for HVAC design. The system population diversity. The system population diversity is the percentage of the sum of zone populations that it is used to size the system. It can be most impactful calculation on the total system outdoor airflow, VOT. To calculate the diversity, the system population PS must be determined. Understanding design. The system population is the maximum number of occupants expected in all zones served by the system. The system population is divided by the sum of all zones population PZD equal PZ calculation of summation of all zones PZ. Example continuations. In the small example of this building, there are only ever 5 workers. Sometimes they are in the office space and sometimes they are in the conference room. The sum of the zone population is 5 plus 20 equal 25 people. The diversity is 5 divided by 25 equals 0.2. Step 4D, the uncorrected outdoor air. International Mechanical Code 2021 Section 403.3.1.1.2.3.3. The uncorrected outdoor air intake flow rate VOU is calculated by multiplying the population diversity D by the sum of the zone outdoor airflow for people and added in sum of all zone outdoor airflow for area. Zone A, office space, zone B, conference room, and here is the table. Illustration 8L, the uncorrected outdoor air intake. Now we add in the uncorrected outdoor air intake flow rate for people and the areas. Step 4E, total system outdoor airflow. International Mechanical Code 2021 Section 403.3.1.1.2.3.4. The total system outdoor airflow is the uncorrected outdoor air intake V out divided by the system efficiency EV. This equation look like this: VOT equal VO divided by EV. Example continuation. The uncorrected outdoor airflow is 109 CFM and the system efficiency is 0.84. So the total system outdoor airflow is 109 CFM divided by 0.84 equal 130 CFM. Study tip. Note that the fraction of the total system air that is outside air is only 130 CFM divided by 1400 CFM, which comes out to 9.3%. This is lower than the lowest primary outdoor air fraction. This reason for this is because of population diversity that was applied. Demand control ventilation. Instead of setting the system outdoor airflow based on the assumed number of people in building. The outdoor airflow can be determined based on the actual number of occupants present the demand. This is often called demand control ventilation, DCV. Often it is accomplished by accounting for the following: people counting, occupancy sensors, carbon dioxide sensors, and a combination of the above. Understanding the code. A design engineer often use ASHRAE standard 62.62.1 for designing the ventilation. ASHRAE 62.1 goes into more depth than what we have covered on engineering the ventilation system. You may encounter ASHRAE 62.1 under spreadsheet and calculations as you review drawing and documents for code compliance. As we come to a close, let's look quickly at ventilation requirements for enclosed parking garage and uninhabited spaces. Outdoor airflow for dwelling units. Dwelling units don't require all of the intense calculation that we have covered. Outdoor air for R2 and R3 and R4 occupancies 3 stories or less is determined by this equation. QOA equals 0.011 floors plus 7.5 NPR plus 1. QOA outdoor air rate CFM. A floor area square feet. NPR number of bedroom not to be less than 1. Study tip: we want you to be aware of this equation used to calculate the required air for dwelling units. Don't worry about using or plugging in the value at this point, this point. If you don't need to calculate the ventilation for dwelling unit or on the test, this is just plug and chug equation. Enclosed parking garage, International Mechanical Code 2021 section 404. Enclosed parking garage must be mechanically ventilated continuously. Illustration 8M, carbon monoxide and nitrogen dioxide detection. The alternative to continuous mechanical ventilation is for parking garage to be ventilated automatically, controlled by carbon monoxide detector and nitrogen dioxide detector. Automatic ventilation had two modes of operation worth looking at. Mode 1, full on, with at least 0.75 CFM supplied per square foot of the floor area. Mode 2, standby, with at least 0.05 CFM supplied per square foot of area. Did you know mechanical ventilation system can be controlled with either manual or automatic controls that operate whenever the space is occupied? Section 405 is in the International Mechanical Code permits this. Think about it. Other occupable spaces next to public garage must be kept at a higher pressure than the garage, so air will not travel from the garage into the occupied space. Ventilation of uninhabited space. International Mechanical Code 2021 section 406. Natural ventilation is required for uninhabited space like crawl space and attic. Fast facts: uninhabited spaces can be mechanically exhausted and supplied with at least 0.02 CFM per square foot of area whenever the relative humidity goes above 60%. Okay, review quiz. Let's see the quiz. Okay, this is our quiz. We already finished it. Question number 1. Outdoor air intake opening are required to be not less than 10 feet from all the following except the property lot line from increase exhaust at the same level of intake presently from the loading above the street. It must be not less than 10 feet above the street. Let's go to the next question. A 200 square foot interior space is being naturally ventilated through an operable window in an adjusting exterior space. What is the minimum unobstructed opening size required between the two? It will be 25 square foot. It's like 4%. Okay, let's go to next. What it is the outdoor airflow required based on population for 1000 square foot fast food cafeteria? It will be 750. Okay, let's go to next one. What is the zone air distribution effectiveness of warm air being supplied through floor diffusers and return through grills at the top of the walls? It is 0.7. Okay. What is the exhaust rate required for 10,000 square foot enclosed parking garage? 7,500 CFM. This here 0.75 CFM as per International Mechanical Code Section 404.1. 0.075 CFM per square feet multiplied by 10,000 square foot. It's given 7,500. Okay, so here, okay, we studied the ventilation system in International Mechanical Code and this for International